Okay, so I make this stiffener be colored red. Okay, notice. So we will try to apply this modeling that will fit this stiffener. So yan ang pinaka-purpose natin ngayon. So for the fillet, so you will notice that we can now calculate f sub 1 and f sub 2. So by algebra, we can notice that f sub 1 is equal to k minus tf. So tandaan natin, ito yung k, ito yung tf, so ito yung natitirang distansya. So yung f sub 1. So that is 6.34 mm. Notice we need to use the design. Do not use the subscript of det kasi detailing yon for drawing. Likewise for f2, that is the algebra for k sub 1 minus half of the thickness of the web kasi kalahati lang naman yung kailangan natin i-consider for us to get this dimension. Yan yung binilugan kong pula. So therefore f sub 2 is 9.145. So ito na yung modeling procedure natin for the stiffener. Diyan tayo magre-decide. Notice, hindi ko ginamit yung radius of fillet na sinasabing least dimension which is 6.34. So if that is your case, try to compare it with my solution. What if that is a circle? Yun nga lang, ito siya. Na wala ng F1, F2. That's already 6.34 by this given kasi the smaller radius of fillet will prevail, which is 6.34 is less than 9.145. So this will be our radius of fillet in the future modeling. But again, naging strict lang tayo na konti dito na kukumpute natin siya based on the availability of F1 and F2 para tingnan natin kung ano yung epekto niya sa inertia sa mga properties ng ating section. So therefore, we can calculate H. So we're talking about this muna. So that is D minus 2TF. So that is 88.48. At yung T naman, syempre, D minus 2 sub K kasi ito yung pinag-usapan natin. Again, do not be confused. This is also our H. Pinapakita ko lang, ito yung H siya na, no, kung walang stiffener. So ito yung without stiffener. So again, ano yung H na pag may stiffener, ang tawag doon yung T. So therefore, ito yung may with stiffener. Okay. So I think this is clear sana that I have discussed this correctly. Okay? Ulitin ko, yung T, yung H din yan in this section kasi may stiffener na given. Ngayon, mapapansin nyo dito, H over TW. So yung H na yan, yan yung T na design. Okay? So tingnan natin, no? H over TW for calibration purposes lang ito. So kung H is 75.8 at ang thickness of the web natin under design, no? Do not use the detailing. That is 7.11. So therefore, we can get 75.8 divided by 7.11 is 10.66. Which is in fact, si ASC sa sobrang rounding off niya, galing sa English unit, at least they are the same. Likewise, for the BF over 2TF, so you don't need actually to use this value for the data because you can compute this on your own. So, ang BF over 2TF is 5.88. But tingnan natin, ang B sub F natin is 103 over 2 times thickness of the flange, that is 8.76. Again, do not use the detailing values kasi sinabi ng AISC to use the design values. So that will give us 5.879. So which is, we are using 5.88. So yun, nag-same sila. So, most likely, dun galing yan. But again, ano yung T na ngayon to? Bakit 66.7? Ang ginamit naman neto ay yung pang-detailing. So, okay, bakit ginamit yung pang-detailing? Kasi yung T na yan, pinapakita sa drawing. So, therefore, ang T na ito para sa drawing ng detailing yan. So, tingnan natin. So, that is the T equals T det, kumbaga, yun na kanyang nomenclature ngayon. So, do not be confused about hindi sila magkaparehas, no? Magkaiba kasi sila. So, ang T sub det is equal to total height in terms of detailing. So, 105 minus 2 times the detailing value ng K, no, which is ang K sub det is 19.1. Okay? So teka, tanggalin natin, nagko-crossover na yung mga values. Okay? So therefore, what you can get here is 2 times 19.1. So iless natin siya sa 105. So we will get 66.8. Again, 66.7 yan, but still, they are the same. Kasi ulitin ko, ba't nagkaroon ng discrepancy ng 0.1? Yung 66.7, nanggaling yan sa conversion from English unit. Samantalang tayo, nag-compute tayo based on metric values na. And again, lahat ng metric values, na-round off na siya from the English values. So, ganyan ang treatment sa T, sa H. So I think I made myself clear on those nomenclatures. So, again, yung T na kinompute natin 75.8 is also H in our calculation. Pagka H na yung nakita nyo, sabi, walang stiffener. Pag T, meron lang stiffener. So, we can now compute for the steel area section. So, meron kang web flange na dalawa, kaya times 2. Okay? Tapos, may web area ka. At meron kang 4 na stiffener. Na ito yung formula natin. So, sinave ko lang dito yung mga formulas natin para nasusubaybayan nyo paano nako-compute. So, therefore, we can get 2466.7838. So, therefore, most likely, nagka-equal sila. Okay? 24, just around 2470 na rin. Pero ito yung mas precise nga lang. Kung gagamitin nyo si, radius of fillet, talagang circle. Makukuha nyo dito, just around 2468 point something. So, therefore, the same sila. Okay? But yun nga lang, tingnan natin sa iba kung ano yung magiging impact niya. Okay? So, same sila na 2,470. The unit is square millimeter as declared kanina sa nomenclatures. Tingnan natin para makompute natin yung beam weight. So, linear weight. As in accordance to ASTM designation A6, A6M-17A. So, under section code 12, permitted variations in dimension and weight mass 1 cubic foot of rolls is assumed to be 490 pounds. So, ibig sabihin, ang density na gusto nyo ipagamit sa atin for the steel is around 490 pound per cubic foot. But in English, sabi dyan, we need to use 7,850 kilogram per cubic meter. Sabihin, pag metric, ito gagamitin natin. So, default constant yan. Lumalabas lang na may relative density siya na less than 7.85. Parang ganun ang kanyang value. So, tingnan natin kung totoo para for validation. Kasi, di ba, gamma is rho g. So, therefore, also, pwede naman ganito na lang, no? Specific gravity or relative density na lang in effect. So, RD, pwede naman yan. That is equal to gamma over gamma of water. So, meaning, that is 7,850, which is density na lang pala gamitin natin of water. So, over at 1,000 kg per cubic meter. So, which is 7.85 ang kanyang relative density. Okay? So, therefore, it is clearly derived, no? 7.85. Pero, meron pa isa nagsasabi ng code na yan. According to a Steel Construction Manual, Section 9 under Contracts, so the unit weight of steel should be taken as 490 pound per cubic foot or 7,850 kg per cubic meter. So, yun nga na may sinabi, the unit weight of other materials shall be in accordance with the manufacturer's published data for the specific product. Malay nyo, may nailagay na bago doon sa steel composition. So, therefore, they have to declare it to the client. Okay? Ngayon, let's compute for the beam weight. So, we know that the beam weight is gamma times the area or density times the area. So, therefore, as we calculate, so, kinonvert natin sa square meter yung total area. So, we'll get 19.3643 kg per meter, which is in the table, that is 19.3. So, therefore, they are close enough. So, they are close enough to consider. So, makikita nyo na may impact pag walang fillet radius, ano. So, wide flanges considers fillet radius. Unless not specified, then compute without fillet radius. Once, hindi siya specified. So, next is to compute the inertia. So, ayan, tandaan nyo, ang neutral axis is equal to plastic neutral. Bakit? Because this is symmetric. So, therefore, we are aware that if the section is symmetric, then neutral axis coincides sa plastic neutral axis. I already discussed that in the previous video lectures. So, therefore, kung susubaybayan nyo yung calculation natin, then you can get I bar x of 4.7478 times 10 to the 6 millimeters to the fourth, kasi ang table natin is times 10 to the 6 based on the nomenclature, and it seems that they are most likely near. 4.7, usually kasi sabi ko nga sa inyo noon, yung values na makikita natin sa metric database is nanggaling sa conversion from English unit. So therefore expect nagkakaroon na ng rounding of discrepancy. But again, they are correct. No? So pag wala stiffener, mas maliit pa dyan. So maliit nga lang yung discrepancy. For about I think 4.68 something. So, ganun din, no, si sectional modulus, na alam natin that is the inertia over the C maximum. So, we are treating the half area. So, D over 2 kasi symmetric eh. Either top or bottom, same lang din naman sila ng kalahati. So, therefore, we can now have sectional modulus 89.5805. That is the stronger sectional modulus, S sub X. So, times 10 to the 3 cubic millimeter. Again, times 10 to the 3, ang unit na ina-understand ng steel design para mag-fit sila doon sa table. Kung gagamitin nyo, yun nasa table. Now, 89.5. So, most likely, they are the same. Now, radius of gyration, R sub X. So, I bar X over area lang yan and then take the square root. Kasi ang origination yan, Ix equals I bar X, no, plus AD squared. Ngayon, if we are going to situate as if there is an equivalent radius, then we can say that the I bar X is set to be 0. Kapag may radius ka equivalent, then we can say that D is the radius of gyration along the X. So therefore, that is a situation. So magiging I X equals R sub X squared times area. And then derivation will now be observed. Then you will get 43.8712 millimeters. So therefore, that is the same with our table. 43.7. Again, a small discrepancy will be acceptable since tama naman yung kinocompute natin. So, ganun din sa I bar Y. So, lahat ng inertia papupuntahin mo sa gitna naman na vertical. So, therefore, by that, you can get 1.5988 times 10 to the 6 millimeters to the 4th. Okay? So, close enough sa value na 1.61 times 10 to the 6 millimeters to the 4th. Okay, so ganun din si sectional modulus along the Y. Again, si bar Y represents the weaker axis kasi by this nomenclature, dahil patayog siya, so we will expect that the properties observed in the X will be far more than the properties of the Y kasi it executes stiffer dimension. So therefore, X will be called as the stronger and Y will be called as the weaker. Okay? So, usually, in-orient natin yung stronger sa mas malakas sa moment. Usually, kapag meron kang gravity loads, okay, pababa. So, therefore, ito yung dapat magre-resist yung X. Kaya, ito yung reason ko bakit, kahit sa concrete design, bakit patayo lahat ng beams. So, at saka bakit yung column natin naka-orient kung saan, yung mas mahabang portion niya, kung saan mas mahaba ang dimension. So, therefore, ito yung reason, because of the stronger and weaker axis notation. Okay? So, just a short discussion. So, therefore, to compute the sectional modulus along the weaker axis or the Y, so you will get BF over 2 kasi doon mo siya papupuntahin naman. So, kukuha na natin ng mga tigkakalahati yan. Okay? So, therefore, I think discussed already from your strength of materials. So, that is 31.0446 times 10 to the 3 millimeters raised to 3. So, close enough, 31.1 sa table natin. Ganun din ulit si radius of gyration along the Y. That is I bar Y over area, but take the square root. Then you can get 25.4584, which is in the table 25.44 yung kanyang value. So most likely nagkaka-same pa rin sila. Okay, so this time let's compute the plastic sectional modulus or Z sub X, considering on the stronger axis or in this statement that is the X axis. So notice that I have shaded the upper region by green. So, dyan tayo kukuha ng analysis since you'll notice that this is symmetric. So, therefore, what you can see at the bottom, let's say there's a value, let's say going to the axis, the plastic neutral axis as value of A2. And A2 equals A1 due to the fact that what you can see above is also the value below. Kasi symmetric. Okay, pantay sila. Ibig sabihin na makukumpute the value. So, therefore, we will try to simplify the computation by having these following. So, since AX is equal to A over 2 times A, and A is the sum of the top and the bottom centroids, and since A1 is equal to A2, then I can simply say that A is equal to 2 times A sub 1. So, therefore, I can simply say that z sub x is equal to 2 times half of the area multiplied by a sub 1. So using the concept of the plastic neutral axis, so getting the area above, so yung x sub 1 natin, it is the distance free from the flange. So hindi ko parang ipinasok ko sa loob na yung stiffener. So therefore, you can compute 44.24. But again, kapag symmetric, di ba, neutral axis is equal to the plastic neutral axis. So actually, you can compute this into another way, ano? So by getting total height, so which is 106 watt over 2 kasi kalahati kailangan equals das k sub 1, no? So therefore what no, it's not k sub 1 but the thickness of the flange by this statement, which is we have 8.76 plus x sub 1. So by this statement, if you got this the same with the 44.24, then I can simply conclude that neutral axis and the plastic neutral axis is coinciding. So by this, 106 over 2 minus 8.76 yields to 44.24. So this concludes that neutral axis coincides with the plastic neutral axis if and only if you have symmetric and doubly symmetric shapes. So, but we are in the interest of computing the z sub x. So therefore, by this I can now use the sense of x sub 1 value of 44.24 millimeters. Okay, so now we x sub 1 to be the value of 44.24. So I can now compute a over 2 times a sub 1. So by transcription of this computation, so kindly follow na lang. So intention is to make the centers to project with the plastic neutral axis. So you can get a over 2 times a sub 1 as 51,636.2276 cubic millimeter. So I have already a separate discussion on how to compute yung titawag nating sectional, plastic sectional modulus. So kindly refer to my past video lecture regarding about collapse mechanism or the plastic yield, plastic theory upon yield and upon plastic condition. So therefore, we can now calculate z sub x, that is 2 times a over 2 times a sub 1, which is twice of the value of a over 2 times a sub 1. Then we can get 103.2725 times 10 to the 3 cubic millimeter, which is the same as to the declared value of 103 in the table. So doing the same for z sub y, so we can have again for symmetric section, because again this is doubly symmetric yung shape natin, because on the y and on the x, so same sila ng pagiging shape. So equal BF, equal TF, equal TW, everything is symmetric. So both sides are symmetric, so it is doubly symmetric. So therefore, you can also have B sub 1 as a value. Ito yung center nung nasa kaliwa, papunta nung plastic neutral axis nung nasa kanan. Nung nasa taas, I mean, or nasa gitna. So again, neutral axis coincides plastic neutral axis along the weaker axis or on the stronger axis. Okay? Kaya, as we compute, so no need for us to compute the x sub 1 or whatever x that we can be computing kasi alam natin gitna na siya. So A2 over A over 2 times B1 will be 23,870.6341. So by using this, again, notice that we have applied only the value of the centers. Okay? Ito yung na-derive natin 7/8 over B. So sa stiffener yan. Kasi di ba sa stiffener natin na ito yung kanyang orientation. Okay? So ibinawsa natin sa 12.7, which is we have this 7/8 of the base B, which is in fact ito yung nakuha nating 12.7. So kinumpute lang natin yung layo. I mean, ito dito siya nanggaling, yung layo niya papunta dun sa center, which is actually baliktad nga yung pagkaka-illustration ko dito. Now, I want you to notice ito yung pinaka-conceptualization. Dito nakaharap, okay? At nandito yung gitna. So, therefore, may value ka naman dito na k sub 1. Okay? Tapos, ibawas mo na lang sa base B na this is 7/8. Dalawa yon, kaya times 2. Kasi taas at baba. No, you have to notice taas at baba. Okay? So, therefore, you can get a value of so by this you can get a value of 47.7413 times 10 to the 3 cubic millimeter, which is close enough to a value of 47.9 times 10 to the 3 cubic millimeter as declared in the table. Okay, so let's compute the other constant, but let's compute a sub naught, okay, or a sub O, which is sabi natin kanina, that is the distance between the flange centroid. So, kunin mo yung gitna nito, kunin mo yung gitna niyan, napalaki yung bilog, okay? So, para dito ko nito-drawing, para hindi na mahirapan mag-visualize, okay? So, kunin mo yung gitna, kahit may stiffener or wala, ito yung H sub naught, which is simply D minus TF na lang, kasi doubly symmetric naman siya, singly symmetric sa isang side na ito. Okay, which is equal yung thickness of the flange. You know, kalahati times 2 is yung buo na rin. So, we will have 97.24, which is 97 mm sa table. Very close enough. Kasi nangyari, na-round off yan from English unit. Okay. So, before we proceed, no, as in accordance to the computation of SW, meron kasing tatlo na SW for 1, subscript of 2, tsaka subscript of 3. So, usually, para sa wide flange, yung S sub W is only 1. So, S sub W 1. Kaya you will notice in this table, isa lang. But if you have C-section, as figure 2 suggests, so apat yan. So, you will notice that in the given table. Okay? Since this is wide flange, so therefore, we'll focus on the figure number 1. Ngayon kung napapansin kayo na may sinasabing Steel Design Guide Series 9. So ito yon. The title for such document from AASC is Torsional Analysis of Structural Steel Members. So ano ba meron dyan? So in the code of such, so 3.2.2 other torsional properties for operant cross-section. So marami kasing way to compute that. So let's focus how do we compute C sub W or the warping coefficient. Tapos may W sub N sub naught o yung tinatawag nating normalized warping function, and S sub W that is described earlier, and QFQW is described as the statical moment for the flange and on the web. Okay? Where H is equal to D minus TF. Note, itong computation H is equal to D minus TF, ito yung H sub naught natin. So, gawin nyo lang, replacing H as H sub naught, kasi nangyari, hindi pa niya nagagamit yung H sub naught na nomenclature. So, ganun talaga, minsan naiiba na nomenclature, but the sense is, H serves as H sub naught. So, therefore, ito H sub O, IYHO squared over 4. So, this is HO BF over 4. This is HO BF squared TF time over 16. And HO TF, okay, and etc. Basta palitan yung H ng H sub O. Okay, by plugging in all the values as seen in the left side, kaya iniwan ko siya dyan for us to apply that. Again, H is equal to H sub naught, sa figure na ito. Okay? So, therefore, as we continue, you can get the warping, the normalized warping function. So, that is, if you plug in all the values, so may formula sa nakasulat dito sa kanan side, sa taas na portion. So, you can get 2,503.93, which is almost near do sa 2,500 ng table, and the warping coefficient or constant for warping, so we can get 3.7794 times 10 to the 9 millimeters to the 6. So almost near sa 3.76 ng table, and S sub W1 na 0.5648 times 10 to the 6, which is sa table is 0.566. Okay, Q sub F and Q sub W are most likely the same. So, 20.3 sa table QF at 50.6 naman sa table ng QW, which is calculation 20.4203 times 10 to the 3 at 50.8266 times 10 to the 3 siya. Actually, itong QF, QW na you don't have to memorize that, kasi makikita mo siya dito, statical moment lang naman. So, to compute QF, so start tayo sa QF. So, ang kakailanganin mo lang dito, of course, we need to get this, yung isang tenga. Okay, note that this is H sub naught, this is over 2, okay, and this is BF minus thickness of the web, okay, And then, this is thickness of the flange. So therefore, how to compute the statical moment for the flange kumbaga, yung pinaka-side lang na naka-overhang. So get the area times the centroid. So BF minus TW times thickness of the web times H sub naught over 2. So meaning, this is the formula as depicted here. Saan na ba yan? Of course, may over 2 pa pala, I forgot. This is BF of minus TW over 2. Kalahati kasi yan. Yan. Half yan, sorry. So therefore, it will become like this. Yan. No? Tama, parehas sila. Ngayon, for the other one, so how do we compute the other one? So therefore, you will need to get the whole, no? Para maging web. So for the Q sub W, sabihin ito yung interest na natin, ano yung QW nito, yung nasa neutral axis plane. So to get that, you need to get the whole. So again, to get the whole, so that is, unahin mo muna yung full flange kasi nalagpasan nyo na yung buong flange. So BF times TF times the centroid H sub naught over 2 plus, no, yung portion naman ito, which is indeed, this is equivalent to, that is H sub naught, no? Kung makikita natin to, H sub naught over 2 minus T sub F over 2 din. So, kasi kalahati eh. So, TF over 2. So, therefore, to get that, that is H sub naught over 2 minus TF over 2 multiplied by ang thickness of the web at ano centroid, kalahati ng H sub O minus TF na merong over 2 parehas. So, pure statics ito. Okay, so therefore, you can get the same formula. So, by derivation. So, therefore, it is easily derived. Okay? So, therefore, yung mga values na to, unique lang yan para sa wide flange. So, may pang C-section, may pang MC, may pang L-shape, etc. na makikita nyo rin sa design guide 9 na actually derivable naman sila. But in the future, we will try to use the other way of computing since we will try to discover other shapes like L, MC, and etc. Again, for the purpose of checking, so we're just computing it right now. Okay, may specification si ANSI Aisc 360-10 about doubly symmetric. Actually, yung computation ng R sub T sub S or the effective radius of gyration raised to 2 equals I sub Y times C sub W over S sub X. Of course, the square root of IYCW pala over S sub X, then equals R sub TS squared. So, naka-square. So, si R sub TS or the effective radius of gyration, yung F2 kasi, no, diniscuss dito, yung computation ng the nominal moment per capacity. As per capacity, kasi may parang MN para dun sa relation niya, dun sa actual moment, which is, meron pa correlation dito si elastoplastic, okay, na diniscuss sa atin in one by video lecture. So, kahit si F3 code na singly symmetric o yung, singly symmetric, that is what we call yung having compacted flange but not compacted web. Parang ganun yung kanyang scenario. So, either way, di naman kailangan si R sub TS to sa F3. So, F4, there's another way, but R sub T na yon, or effective radius based on non-compact condition for the web and non-compact flange. Parang ganun nangyari. So, either way, basta doubly symmetric ang pinapakita ng table natin, since this is doubly symmetric, then it is R sub TS based on this. Then, upon application, you can have 29.4576, which is very close enough sa value na 29.5. So again, this is dependent on what type of shape you are computing. Again, for doubly symmetric or wide flanges, we are using this. All wide flanges. Okay, balikan natin konti yung torsional guideline for structural steel members kasi may theta value ka dyan na kailangan i-understand. Okay? So, ito yung code niya. Medyo, yung T na to, hindi siya yung T na kinumpute nito, no? They are not the same. Okay? So, again, the T represents torsion. Kaya nga, ang daming magkakapare sa letter, kaya inaayos eh. So, dapat ma-understand nyo, may T para sa database value at may T for computation. So, yun nga lang, manonotice natin na medyo may kahirapan na konti, may relationship coefficient of warping at si T at si J, si G, theta prime, theta triple prime, as differentiable set boundaries for the equation. Depende sa shape, depende sa direction of rotation, etc. So, medyo mahirap. Ngayon, ginawa, there will be some equations to be adapted. Okay? Okay, so according to ANSI AISC 360-10, so they have described yung value ng J or torsional constant that can be approximated by the sum of BT cube over 3. So therefore, kung susundin natin yan, kung walang stiffener or yung titawag nating fillet, na apat na fillet, ano, as we already counted, so we can compute J as approximately equivalent sa BF, TF cube, okay, over 3 plus, let's say, if you want to use H, ano, or simply say, sabihin na natin, total depth minus twice thickness of the flange, which is H. Ito yung H na without stiffener. Okay? So, i-exclude muna natin yung stiffeners and then multiplied by thickness of the web and nakakube yung thickness over 3. So, therefore, ito yung magiging base computation. So, i-disregard yung sense nung stiffener or yung fillet. And also, in accordance to Design Series Guide number 9, ganun din yung sinasabi in 3.2.1 of the torsional constant J. So, therefore, that is the equation. So, by the way, yung formula na ito is what we call Saint Venant's equation. So, ang gusto kasing gawin ni Saint Venant, Saint Venant's equation for this, okay, ina-assume niya na yung mga decimal for about 10 thousandths of place. Let's say, if you have a value of 15.83, 42, 64, etc. So, marami yan. So, if you're going to count, tenths, hundredths, thousandths, 10 thousandths. So, kumbaga, ito yung pagdating dito sa tens, hundreds, thousand, 10,000. So, somewhere here. So, kung ito yung cut-off portion niya, this is considered negligible. So, parang hindi na siya nagkakaroon ng malaking factor, okay, doon sa computation. So, therefore, yun ang kanya kinukonsider na ito daw, pagka kinukonsider natin, is just only approximately the sum of BT cube over 3. The sum of it. Okay? So, yan lang yung sinasabi na equation kapag walang yung tinatawag nating stiffeners. So, kanina nasabi natin, di ba sa AISC provision na pinalabas no February 2017. So, meron ka equivalent fillet radius. So, ang consideration yan, sana, kung ang F1 mo at ang F2 mo are the same. Ngayon, di natin magagamit yung modeling ng 6 degree kasi medyo mapapadirect tayo na konti, but adapt na natin yung code natin na you can use the smallest fillet to be the radius, which is in fact that is 6.34 because 6.34 is less than 9.145, no? Kung ikukumpara ko itong dalawang to. So therefore, itong R na to, itong magsisilbing value sa computation na kailangan ni AISC. Sige, in accordance to design code, no, series guideline 9, C.3.2, so the following equation for the J, a more accurate value than the simple approximation, yung sitawag natin Saint Venant. So, di natin muna gagamitin since given naman yung full table. So, ginagamit na si Saint Venant pag hindi binigay as a table yung value, so you can compute it manually. So, therefore, pag walang stiffener. So, pag may stiffener, ito yung setup. Yan. Okay? So, nadagdagan lang ng konting equation. So, nagkaroon ng correction factor. So, as we compute, yung R represents radius of the fillet. For R sub alpha 1 and D sub 1, o yung diameter equivalent, yung sa bilog sa baba sa flange area. Okay, then flagging in, ano? Makukuha natin 62.8905 times 10 to the 3. which is close enough do sa value ng 62.9. So imagine, kung wala tayong correction factor, medyo liliit pa yung values natin, pwede lumaki. But usually, hindi siya malapit sa 62.9. Around 50, I think, yung na-compute ko before. So therefore, importante na i-consider 62 sa rotation kasi malaking factor siya sa pagkakaroon ng rotation theta pag nagkaroon ng involvement si torsional threshold. And the rest, no, yung makukompute natin na PA, PB, PC, PD, kung naalala nyo, sinabi dito yung design guide, series 13, so related po ito sa fire protection. So we no longer discuss this because this is not part of our design computation. So therefore, if you want to know those things, then you may refer to series 13 no, of under fire protection. So may another guideline for that. But that is being delimited in this video lecture discussion. So we have already completely identified what are the important parameters that we need to compute. Kaya that's why nakikita mo yung importance ng pagkakaroon ng table na gagamitin lang natin in such a way that it can be used in our design computation starting the next video lecture. So thanks for viewing. I hope you learned new things today regarding the strict computation of those values as found in the table, and as a tradition, you have been neurorized, and see you in our next video lecture. Next topic is how do we identify if the section is compact or non-compact. This will be a gateway for us to better understand how do we compute the nominal moment capacity of the section. Ito na yung very important, yung very interesting portion. Doon na natin ma-design kung okay ba or hindi yung section na pinili natin under flexure, under load condition. So, see you in our next video lecture.